So how do we analyze the block design? Let's take a look now at some real data to see how we should analyze a factorial experiment that includes a block. Here we're going to consider the effect of BHA treatment on liver EROD activity in mice, which possess different genotypes. And this is a data set that comes from a 2003 paper in Transformological Science written by Michael Festing. This is a rather extreme example of design because, in fact, each combination of the factor levels was measured only twice in total and only once in each block. In this experiment, 4 different mouse genotypes were subjected to treatment with BHA or a control injection with saline for a total of 8 mice in each block. The first block of mice was measured, and then subsequently 2 months later, the second block of mice of the same size was measured. So in total, that makes 16 mice were used. And this is an example of a randomized complete block design because all factor level combinations appear in each block, albeit only once. These are the values for the liver EROD activity for each mouse. Can we do a reasonable analysis with such little data? Let's find out. First, what we're going to do always is plot the data. Here we show the mean EROD activity of each combination of factor levels averaged over the 2 blocks. We also show the standard deviation of the measurements. Note, however, though, with so few data points, plotting means and errors in this way, means and deviations in this way, is considered by many to be a bit misleading about the quantity of data that we have. With so few points, it's better practice instead to plot the raw values themselves. And this has an added advantage for us. It allows us to see that there's actually a considerable block effect going on here. The values of block 1, which are the circles, are always higher than the values from block 2. Now, this nuisance variation isn't important to us. We don't really care that the EROD level was higher in block 1 than block 2, but we do need to account for this to understand how BHA affects EROD. As we saw before, we can account for the block effect by including block as a factor in the model. Looking at our ANOVA table, we can indeed see that there's a large amount of error coming from the block effect. When we account for this, we see that there is an effect of BHA on liver EROD, and also potentially an interaction effect between mouse genotype and BHA treatment as well. What happens if we don't include the block effect? Well, as before, our conclusions change. This is because the error apportioned to block again gets shunted to the residual error term, which means that our F values decrease and our P values increase as before. Hence, not accounting for the block effect, as might be tempting to do because of the small sample size, has a big influence on our inference. If you want to understand more about how the F value is calculated, do have a look at the link included in this slide. Finally, as an aside, we can also convince ourselves that the block effect model is actually a better fit to the data. We can do this by using the ANOVA function to compare the 2 model fits themselves. Although by accounting for the block effect, we lose a degree of freedom, estimating that block effect reduces our residual sum of squares and thus produces a better model fit, as indicated by this p-value. Again, here's the code that you can use to try this yourself. Note, however, though, that the plots I produce come from a package called ggplot, which is a package in the larger package of packages called the tidyverse, which you might need to install before running some aspects of this code. The tidyverse is a great collection of packages which extends a lot of the functionality of R, and if you're interested in some of these more in-depth and complicated approaches, do have a read of the 2 links provided in this slide as well. All right, let's summarize what we've learned about block designs. Block designs are typically used to account for otherwise uncontrollable error, and these can often arise due to logistical or financial considerations that need to be made when designing the experiments. Blocks are analyzed as a factor, which allows us to apportion variation that we don't care about correctly, thus accounting for noise and variation that is not necessarily of scientific interest. Many different block designs are possible, and here we've covered just a few, which include randomized complete block, incomplete block, and balanced designs. And we also learned a little bit about split plot designs used in the ecological literature. Furthermore, there are tools that exist for planning and analyzing some of these more complicated block designs that we need to construct. Finally, now let's look at a few other considerations that have to do with factorial and blocking designs. One is that factors can be more complex than a simple label. One those of you who are in the bioinformatics field might come across frequently is something like position within a phylogenetic tree. Furthermore, our experimental variables do not necessarily need to be factors in every case. We can also include continuous variables as explanatory variables in a type of model known as an analysis of covariance model, or ANCOVA. And for more details on this, have a look at the link in the slide. This next item is something that we'll come across a little bit more in another session, but both factors and blocks can be treated as either fixed variables or random variables. And this has to do essentially with how the F statistics are calculated, but we'll come on to this more in a later session. Finally, an alternative approach, rather than using blocking, is to incorporate control variables into your model. And so where blocking is about controlling for the known unknowns, instead what we could do is measure other variables related to the experimental conditions to try to account for some of these additional sources of error. And this is an approach often used in ecology, where, for example, you might take the temperature or moisture levels at a site and use this to explain some of the variation in your response variable. For an extended discussion on this, see the link below. And finally, here are some additional resources that might help you when consulting on whether to use a factorial design or a blocking design in your own research. Thank you.